There we go. Questions? Or someone about to come up with a question?
Could you do a little bit more elaborating on the parallels and I can't remember what they're called.
So you said parallel, so I'm thinking parallel capacitors, parallel plate capacitors, or parallel between two different, seemingly unrelated things.
Two different things, but basically there's parallels and then like, I guess they're almost in like a straight, I can't remember what it's called.
Series?
Yeah, series.
Oh, parallel and series?
Yeah.
Okay. Any questions related, more related to the test? Because parallel and series would be the next test. Okay. Go.
I guess, do we need to know how to like, I guess one of those questions where we derive our own equation to then use it on another problem type of thing?
Oh, like on the master set?
Yeah, something like that.
It's fair game. I tend not to do that as much as I did. And so it's more of setting up the situation with numbers and you solving it. Does that answer your question?
Yeah.
Okay. All right, so parallel series capacitors. What's the impetus behind your question?
There was one question in particular about, arranging, on the master set, arranging the, I did the master set.
Is that,
It's like arranging the charges or arranging the capacitors so that it equals.
so given five capacitors, draw a configuration that would yield a
Yes.
capacitor. That's master set 27, isn't it?
Yeah, I don't think we've covered that in class yet.
Yeah, we're gonna do that today.
Okay, I thought that was the master set we just turned in.
I was thinking 26 is due today.
Oh,
Did you do 27 first?
I think I did 27.
All right, so we'll get to that. You'll have a chance to
Okay, no.
take that one back. 26, if you can get 26 to me, that would be good.
When can I get it to you and just, like,
Thursday?
what?
By Thursday, is that realistic?
Yeah. I can
Okay,
do that.
yeah, Thursday.
I'll connect this back.
So when everyone else is struggling with 27, you can look at them and just laugh. And the rest of you, while he's struggling with 26, you can just sit back and laugh.
I think I might have turned in 26 last week.
Oh, okay, all right, so you're just ahead of, so you can just,
I think I missed like 25 or something. Somewhere in there.
I was thinking I had, all right, so there's, you're 24 right there. And you're 25. So I just have 24s and 25s here. Well, I would not have graded 26 yet, so if I have yours, it's separated from the herd.
Okay, I'll get to it.
If, as you start looking at it, you go, I know I did this, then just send me an email saying, hey, could you look again?
Yeah.
We'll eventually figure it out.
Okay, absolutely, thank you.
All right, but we will answer the question that he asked. He was just ahead of the game there. So, but first, let's just start out with parallel plate capacitor. And although orange works really nicely here, not as easily seen, so blue's working today. Yeah, there we go. All right, so no dielectric in between. Let's make this really huge, 10 meters by 10 meters, and I got 1 centimeter in between. And let's see, let's make this a 12-volt battery. And all right, so we're going to start with that. Let's sort of go down the list of equations that we have when dealing with parallel plate capacitors. So I know that capacitance is defined as the charge, because you'll have one plate with Q, another plate with negative Q, and this formula works for any type capacitor. Q over the voltage it takes to put there. So it's basically the charge per volt. We have that the potential difference between the two plates is equal to negative E dot delta X. And the negative is indicating that I got a battery here with a positive and negative side. And as you hook it up, we have electrons being put onto the plate, making this negatively charged. When an electron shows up here, it drives an electron off the other plate, making the plate positively charged. And there's a potential difference between them. I've got all this negative charge, all this positive charge. So if I'm going from the positive plate to the negative plate, I'm going to lose potential. If I'm going from the negative plate to the positive plate, I'm going to gain potential. So if my electric field is going from the positive to negative plate, my electric field, the way I've drawn it, is going to be going to the right. So if I'm going in the direction of my electric field, I'm going to be losing potential. So that's the importance of the negative sign there. This is also a specific case of the fact that the voltage between 2 points is the integral of E dot dx, or dr, d whatever you're using for position. But in our nice ideal situation here, if these plates are close enough together, given the size of them, typically 10%, if the distance between them is less than 10% of one of the dimensions of the plate, then you can consider that close enough to the infinite plate approximation. I know that the electric field strength from the plates is equal to sigma over epsilon sub naught. The total electric field is sigma over epsilon, and the difference being the fact that epsilon would be the permittivity of whatever the medium is in between. So if I get nothing in between, it's the same as epsilon, thus sub naught. And for parallel plates, C is equal to kappa epsilon sub naught A over T. And I guess the relationship between epsilon sub naught and epsilon, that epsilon is equal to kappa epsilon sub naught. So these are the equations that we're working with here. So the quantities, capacitance, we should be able to calculate what the capacitance is of this. We should be able to figure out what the charge on it is, what the voltage is, what the electric field strength from the plates is, and the electric field strength total. We could also find the electric field, the back electric field coming from the dielectric, but I'm not going to add that to one of the things here. We will mention it at some point. So what we're about to step into here is we're gonna start with this basics, and then I'm gonna start making adjustments to it, and so we should be able to calculate how things are affected as I adjust. But let's just start out with, what is the capacitance? And how would you find it? Or how would you find it, and then what is the capacitance? Which formula would we use?
The first one, C equals Q over delta V.
Do we know what Q is?
No.
All right.
We use that fifth one, because we know the distance.
Yeah. So to start out with, we're gonna be using this one, then we're gonna use the one that you're suggesting in order to find the charge.
Okay.
And just a side note, the first equation up here is always true for whatever capacitor, so later on when we talk about cylindrical and spherical capacitors, we'll be using that first equation. The last equation here is true for the parallel plate capacitor. All right, so kappa in this particular case, what is kappa to start with?
Just one.
1, yep. Times epsilon sub naught, which is the constant. Negative 12. That's Coulomb squared per Newton meter squared. Times the area, 100 square meters, divided by the distance, 0.01 meters. We conveniently have a bunch of ones in there, that's nice. So we end up with 8.85 times 10 to the negative 8
Yeah.
units.
Farads.
So 8.85 times 10 to the negative 8 farads. Questions how we got that?
Where did that kappa value come from?
Kappa is the dielectric constant, and so it is basically the ratio of what the actual permittivity of the medium is it's going through versus free space. But since we're starting with nothing in between free space,
see.
it's
Okay.
1. And for the paper products and things like that that you were using, I think it's between 1 and 2 for paper. All right, define charge. As Devon had mentioned earlier, we have C is also equal to the charge over delta V. So actually, let's do delta V first. What is the voltage between the two plates? Or from one plate to the next?
Well,
And so now, the charge has to be capacitance times the voltage. So it's 12 times that. If only I'd done a 10-volt battery. Anyway, so what is it?
1.06 times 10 to the negative 6 coulombs.
Okay. And again, pointing out that the big C at the end of what I just wrote is not the same as the big C in the first line. One is a unit, one is a quantity. All right, so the electric field from the plate, or the electric field in between. What is, yeah, I've got it up there. So it's sigma over epsilon sub naught. What is sigma? sigma is Q over the area, surface charge density. So my electric field strength is Q over A epsilon sub naught. So Q 1.06 times 10 to the negative 6 coulombs divided by 100 times 8.85 times 10 to the negative 12 coulomb squared per meter squared. Oh, so putting units in, that's all. 100 square meters. That's roughly 1,200
Yeah.
units.
Units per coulomb.
And what is the magnitude of the total electric field in the middle?
Is it the same because there's no dielectric?
Absolutely. Now, if you get into a test or quiz type situation and given a problem like this, or even on the master set, and given a problem like this, and you suddenly blank, you can always just plug in everything that you know and see what you can solve for. All right, and leave that up. Any questions before I erase the work we just did? All right. Now, let's change it around. I now stick a dielectric in between. And that dielectric takes up more room than originally thought, so the plate's spread now to 1.5 centimeters. And the dielectric constant for this is, we'll make that a 2. So I'm putting a dielectric with twice the permittivity, and it pushes the plates out just a little bit, pushes the plates out by 50%. So the first question is, what is going to be the exact same as before in terms of our 5 quantities here? Yep. So that stays at 12 volts. And
Q? No. The Q would be the same, wouldn't it?
probably not. I mean, part of, you've got all these electrons that are sitting on the plate, sitting on this plate here, that are there because they're being sort of forced away from the negative charges down here, but also attracted to the positive charges. So you get this nice balance. And then when I push them apart, the attraction to here is not quite as strong as it used to be. So, but the dielectric will also increase it. So we potentially will get a change for it. All right, so what can we solve for now?
You can do C.
All right, so I guess back to this formula down here. Since we can't guarantee the charge is the same. So D is increased by 50%, Kappa is increased by increased by 100%. So Kappa's double, this is increased by half, or 1.5 times the original, 2 times the original. So that would be 4/3 of the original. Or could just go classic 2 times epsilon sub naught times the 100 divided by 0.015. Something times 10 to the negative 7.
I got 1 point.
At 1.18.
You had 1.18?
Yeah.
Oh, I realized what I did wrong there. All right, so 1.18 times 10 to the negative 7?
Yeah.
Where did you get, I got to the -9. It's the -12th power, right?
Yeah.
Well, the epsilon sub naught is to the negative 12.
Right. So E naught times 2 times 100.
Divided by 0.015?
0.015.
Yeah,
Oh,
because
because
it's
it's-
that's in
okay.
centimeters over there.
Okay, I get it,
Okay.
sorry.
All right, so we have the new capacitance. So the capacitance increased because we did have these 2 changes. One diminished it and the other one increased it. So ultimately a net increase. Charge, same thing as we did before, using the first formula right there. Capacitance times the voltage. So 1.4 times 10 to the negative 6-ish. One point 38.
Got 1.41.
1.4.
1.42, sorry,
1.42.
to the -6.